Okay, lecture 8.3, the simplex algorithm. Simplex algorithm, or method, is an iterative technique for finding the optimal solution of the linear programming problem of equations 8.9 and 8.10, which are the equation you want to optimize, which is 8.9 from the previous lecture, and the equations that are defining the constraints, 8.10. The details of the algorithm are somewhat involved, but the basic idea is to start at a vertex of the feasible solution space S and traverse an edge of the polytope that leads to another vertex with a greater value of F. Then repeat this process until there is no neighboring vertex with a greater value of F, at which point the solution is guaranteed to be optimal. Rather than present the details of the algorithm, it's literally just this like really boring linear algebra mechanical process of like, take this row and multiply it by that row. And it's just, I got bored reading it. And I was like, this is so boring. I don't even want to teach you guys. I don't think you get any insight into it from doing that algorithm. And
developing our own algorithm, that's what we need to do like that.
Yeah, and then you need to understand it. I mean, at that point, you should really go through, why. And there's this whole thing where you draw a big table or matrix, and then you identify a row that has a certain quality to it, a certain aspect to it that you're looking for, and then you identify a column, and then you pivot. Do this pivot operation on that. So it's just like, it's not Gaussian elimination, but it's very similar to Gaussian elimination. You just go through, operate on the rows and the columns, and then you get a new, you essentially, what you're doing is you're moving to another vertex. You're using these linear algebra techniques to move from one vertex to another vertex, and then see what F is, and then do it again. So it's cool. I mean, it's a really cool algorithm, and it was very important in the development of optimization. But it's kind of boring in the details. And I don't think it really, unless you spend a lot of time unpacking the details, you don't get a lot more insight into the algorithm. So I'm going to skip the details of the algorithm. So rather than present the details, we choose to show an example using Python. There have been some improvements on the original algorithm that have been implemented into many standard software packages, including Python's SciPy package module, scipy.optimize. Okay. There's this other Python package that is called Pulp, which is for doing linear optimization problems, so just doing linear programming problems. It's like specifically for that. It's more popular for doing linear programming problems. However, SciPy Optimize has other algorithms in it that are very useful for optimization. And so I preferred to introduce you guys to the Optimize one. They're equivalent in a lot of ways. The Pulp one has some niceties that the SciPy Optimize's linear programming module doesn't have, but nothing that we needed. So I recommend using SciPy Optimize. It also does stuff like the gradient descent that we did in the preceding lecture. So we wrote our own in the preceding lecture, but you could also use SciPy Optimize for that. So like, what's the MATLAB function? fmin_con. SciPy Optimize does a lot of the same stuff that MATLAB's fmin_con does. Yeah, so there's that. So we're going to use that, and I think that if you're going to do a lot of linear programming problems, then probably check out Pulp. But if you're just going to do an occasional one, then I think using the SciPy Optimize is just as good. So. Great, so let's do an example. Maximize the objective function, linear one here, c.x, where I give you c, subject to the constraints here. So we've got two constraints just on the variables x1 and x2. So we called these boundary constraints, or bounds, above in the preceding lecture. And then these are all inequality constraints. I didn't put in any equality constraints, but you can also use equality constraints in with this method, using this software package. So first, load some Python packages. We're going to use the linprog, linear programming module of the optimized module of the Python package scipy. Okay, so a couple layers there. And we'll use NumPy, of course, and matplotlib to do the plots, and then this IPython display for doing some of the nice visualization of the equations. So, encoding the problem. Before we can use linprog, we must first encode equations 8, 11, and 12 into a form linprog will recognize. We begin with f, which we can write as c.x with the coefficients of c as follows. So we put in 5 and 2. Well, 5 and 2 were the ones that were given, right? 5 and 2 for c. I put in -5, -2 because linprog minimizes f, and we want to maximize f. So I just negated f. Just flipped it. I have no idea why linprog minimizes, because in most linear programming problems, you're maximizing f.
The same as mincon, the same.
Yeah,
Minimize.
it's minimized, but that one makes more sense because a lot of times you're looking for a minimization when you're doing certain types of problems. Anyways, it's weird. It's weird because almost every simplex method presentation that I saw was always maximizing. For whatever reason, this thing minimizes, so you have to flip a sign. Okay, we've negated that for that reason. Now let's encode the inequality constraints. We will write the left-hand side coefficients in the matrix A and the right-hand side values in vector A, little a, such that, oh, and I used B here. This is supposed to be A. Notice that one of our constraint inequalities is greater than instead of less than. Let's see. It's this one right here. Okay, so when we encode that in, so we're going to encode these three in, what we're going to want to do, how do you flip an inequality sign?
Multiply by -1.
Yeah, multiply both sides by -1. Multiply the inequality by -1. That's what we'll do. So this will be +8, +1, +75 when we encode it. So the coefficients are going to be 4, 1, 1, 3, 8, 1 for A matrix. 4, 1, 1, 3, 8, 1. And then on the right-hand side of all those inequalities, we're going to have 40, 35, 75, which 40, 35, and then remember we negated this, so 75. Okay? Great. Now we need to define the lower and upper bounds of x. The function linprog expects these to be in a single list of lower and upper bounds of each xi. Okay, so it's a little bit specific in how it requires it. So I create a list, LU. This is the range of valid values. These are the bounds, right? These are the x1 bounds. And these are the x2 bounds, which were given. So 0 to 10 and -5 to 15, which are given here. 0 to 10, -5 to 15. Okay, so those are the bounds. All right, we want to keep track of each step that linprog takes, and there's a hook in there for this. We can access these by defining a function callback to be passed to linprog. So we're going to store the value of x, so it has two value, x1, x2, for each step that the program takes. So we define callback function. We use global x. It's not great to use global variables. I typically don't use global variables, but callback can only be a function of one variable. It's a restriction put on by linprog. So I didn't try, but I just followed the docs, and it said that you can only have one variable or one argument. So I left the one argument as being the result that the program's going to spit out at every step. And well, I could have. Now I'm remembering that I could have put it into a lambda function. That's what I probably should have done. Anyways, whatever. I used a global variable because sometimes global variables are helpful when you forget you could use a lambda function. So global x, and then I'm just gonna append to the x list every time through. There's a little nicety here where I have to copy the list in order to append it. Otherwise, it'll just insert the same list in everywhere, and it's really annoying. But it's a thing that happens when you use these methods on functions that operate on self. Sometimes it'll like back propagate, and you. It took me a minute to realize why this was happening, and then I finally realized. So you have to copy that to append it. Great. So here we go. I want to print also the iteration number that we're on and what the current value of the vertex, which vertex we're at, essentially. What are the coordinates of the vertex that we're at? Now we need to call inprog. We don't have any equality constraints, so we need only use the keyword arguments A, U, B, which is the upper bound A matrix. Okay, so A is what we called it. And then the B upper bound is the right-hand side of those, which we called little a. For demonstration purposes, we tell it to use the simplex method, which is not as good as its other methods, which use better algorithms based on the simplex method, but they've improved it over the years. So there are a couple that it has available that are very good. The simplex method is almost never used anymore in its original form, but I'm telling it to use it in its original form just so that we're using the one that I'm introducing here. What I'd recommend is that you use there's a default one that is better, more efficient. I would recommend. But it uses it's based on the same idea as the simplex method. So it goes from one vertex to another vertex, and then it tries other vertices that are nearby, and it tries to increase it. Okay. Great. So now I'll call inprog, and I'll hand it the coefficients of f, okay, our function coefficients. Hand it a, hand it little a, hand it the bounds, lower and upper bounds of x1 and x2. Tell it to use simplex, give it our callback function that we defined. And then I also turn x into an array afterwards because it was a list. I want it to be an array because it's easier to work with arrays when you're going to do stuff like plotting and whatever. So lists are fun, but arrays are a little nicer to work with, NumPy arrays. Okay, so here's what happens. Iteration 0, it starts out at 0, -5, which is a vertex of it. You can recognize it as being the lower bound of x1 and the lower bound of x2. Okay, so it starts off there, and then it moves to 10, -5 as the next vertex. Then it moves to 8.755 as the next vertex. And then it goes to 7, 9, we'll call this vertex. Okay, and this is iteration 3. It tries again, it tries to go to another vertex and increase the value of f. it ends up coming right back to the same vertex, and it's the optimal one. And then it tries once more. I actually don't completely understand why it tries twice here. I know that on the last one it always prints it twice. It doesn't print it twice. It goes back to it calls that calling function twice. So there's that. There's one extra one here that I can't explain. Well, it's actually the extra one is why it increased from 4 to 5. So this is the one that I don't know. I don't know why it does this one. Could be an idiosyncratic aspect of the way that it is doing the numbering of each of these. I don't quite know. But I tried to get more information about what it's doing at each case, but I couldn't figure it out. This is just supposed to be x. So the optimal solution, fx, is the result.x and the negative result.fun. So we had to do the negation because, once again, we minimized the negative, so we have to take the negative of the outcome. So because of the max hack, I was calling it. And we got that we ended up at the vertex 7, 9, and the optimum value of f is 57. Okay. Okay, so this is the explanation of the callback coming multiple times. Okay, plotting. When the solution space is in R2, it is helpful to graphically represent the solution space, constraints, and the progression of the algorithm. We begin by defining the inequality lines from a and little a over the bounds of x1. So that's what I do here. I just unpack essentially the coefficients of a line, and I create the two endpoints of the line and store them in x2. Okay. We now plot a contour plot of f over the bounds of x1 and x2 and overlay the inequality constraints and the steps of the algorithm stored in x. So plotting is always half of the code in these things because it's always messy to do the plots, but the idea is do a contour plot of f and then start to overlay things. I put a bounding box around, so I bounded the x1 and x2, so there's a lower and an upper on each. So I put those lines in, and then I put in the inequality constraints, which will be lines that'll be angled in x1 and x2. And then I finally plotted the steps the algorithm took. So those x values that I saved. So what this results in is a very pretty plot. That, yes, took me way too long. I don't like to admit how long these plots take to generate. But thank you. Thank you for appreciating it. It took a long time to make it.
Much better than MATLAB plot.
Yeah. Well, yeah, so it's very pretty. So let's unpack what's going on here. First off, we've got the contour plot. It's always just going to be stripy when it's linear, right? So in this linear stuff, it's always going to be stripy. Just straight line stripes. And actually, what we recognize is that these lines, these contour lines, are the level sets of our function f. They're the level sets of the function f. So they have the same value along all this. So actually, the boundary between this blue and this teal, let's call it, is 30. So it's this blue and this teal. So f equals 30 along this line here. Okay, so f equals 30 along that line. And so f equals 45 along this line, x equals 60 along this line. So we are subject to the constraints. So this actual frame here are the constraints on x1 and x2. So x1 can go from 0 to 10, x2 can go from -5 to 15. So we're bound by those constraints for our solution. It's further whittled down by these three inequality constraints. Okay, 1, 2, 3. The three inequality constraints. And so these are all upper bound constraints, and so we're left with this region in here that is our S. Okay, so S is this entire region. Okay, we started out at 0, -5, remember? And we followed the red line over to 10, -5. Then we went to the next vertex that is a boundary, on the boundary of S, and we were at 9, 5-ish, and then we jumped to here, which is where we ended up sticking multiple times, right? It tried to move along the edge to here, and it ended up coming back there. Because look at what F is here. F is 58 or whatever, and F over here is in this blue band, so it's between 15 and 30. So that's going to be smaller. So the simplex method did this traversing up to there. So that's the method, and that's if you're working with, I mean, you could have any number. Actually, you can use this code to show you this graph for any number of linear constraints. But you can only go up to 2 variables to show it. You could do a 3-variable one. At first, I was thinking about doing a 3-variable one. But you can't overlay F very easily on a 3-variable one. So you could do like a 3D cloud density plot. I was thinking about it, and I was like, that's going to be 3 times as much time. This one took enough time already. So, yeah. So this is our representation of what we were doing. We were looking for this point. Now, obviously, if you have 2 variables, you could just do this plot, and you could identify which one's the optimal one. Or if you just have this many variables and you only have a handful of constraints, you can just try all the vertices, right? Not that many of them. You can just test out F at each of the vertices, and you're good to go. But the simplex method, when you get to high numbers of variables, like imagine if you have hundreds of variables, which is possible, and especially in like a big plant logistics sort of thing, or like shipping, or like, you know, Amazon tries to optimize where it has its products because it knows kind of the average demand in different places, that type of thing. So many variables go into it that you have to have a search method that's not just a naive, exhaustive search. Okay, so any questions on this? All right.